All right, section 9.3 is what we're going to do whenever we're testing a claim about two means. In part one, we're going to look at what to do with two samples if the standard deviation is unknown and not assumed to be equal. So two samples we say are independent if the sample values selected from one population are not related to or somehow paired or matched with the sample values from another population. They're dependent if they are paired. For example, what we talked about in 9.1 with measuring the effectiveness of a cholesterol lowering drug. If you take a before measure, apply the treatment, and then take an after measure, those would be dependent variables because you have before and after measures. Or you could do twin studies or look at husbands and wives or other types of dependent variables. So for example, an example of independent samples, researchers investigate the reliability of test assessment. On a group consisting of 30 students who took proctored tests, the second group consisted of 32 students who took online tests without a proctor. And then we looked at those two results, those who took a proctor test and those who didn't. These samples would be independent because the subjects were not matched or paired in any way. Dependent would be students of the author collected data consisting of heights of husbands and heights of their wives. 5 of those pairs are listed below. The data are dependent because each height of each husband is matched with the height of his wife. So those would be dependent because we're looking at heights of couples. Independent versus dependent. That's a conversation we've had in the past. The notation here, just like it was with the proportions, if you see a subscript here of 1, that means that we're looking at the information for the first group, whatever we define the first group to be. And then if we change that subscript to 2, then we're looking at the information from the second group. Now, the requirements in order to use the test that I'm going to show you is that the standard deviations of both groups are unknown and no assumption is made about the equality of the standard deviations. The two samples have to be independent of each other. They're simple random samples and either or both of the following conditions are satisfied. Either they are both large samples, both of them having more than 30, or they're both normally distributed. They're coming from populations that have normal distribution. The hypothesis test for the two means is going to be that the two means are equal. If you're looking at a null hypothesis here, that would be that mean 1 is equal to mean 2. Another way of writing this is that mean 1 minus mean 2 is equal to 0. These are equivalent ways of writing the same thing. When we're doing the tests here, we're going to go to stat and then scroll over to test, and then we're going to go down to the two sample t-test. Because nothing is known about the standard deviation of the groups, we're going to be using a t-distribution. So then this is what your input screen would look like, and you scroll down, this is input 1, and there's more information that follows, so we have to go over to a second screen. Notice at this point they're repeating right here. These values are repeated. Those are where there's overlap. Always leave your pooled value at no whenever you're putting your data in. This is a default. Do not change unless you know for sure your data are pooled. The difference is not necessarily significant, but we would rather err on the side of caution and assume a larger variance than what's possibly necessary. So that's why we leave this on no. The test statistic for the two means are independent samples. Whenever we're doing a test of hypothesis, their degrees of freedom is going to be a simple method in this book. It's going to be the smaller of either your first sample minus 1 or the second sample minus 1. Pick the smaller one. The p-values are going to come from the calculator, and the critical values, we're going to use this method right here in order to find our critical method. We'll use this for our degrees of freedom as well. The smaller of n minus 1 for either the first sample or the second sample. So when we're doing the inverse t, we'll put our alpha level here, and then this number right here will be the smaller of n sub 1 minus 1 or n sub 2 minus 1, because it's possible your samples will have different numbers. Confidence intervals, we take our point estimate minus the error. This is our point estimate, and this is our point estimate plus the error for the upper bound. Here's the formula for how we calculate the error. We're not going to have to do this by hand. We will do confidence intervals, but we'll do them on the calculator. So for the test, if you want to do a 2-sample t interval, make sure the last letters on the calculator are INT and not test. So we have 2 samples, either interval or test. These are the keystrokes I took to get to this test. This would be input 1, and this would be input 2 for the confidence interval. Looks very similar to what we would do for the input on the test. Caution: before conducting a hypothesis test, consider the context of the data, the source of the data, the sampling method, and explore the data with graphs and descriptive statistics. Be sure to verify that the requirements are satisfied. Remember, there's no amount of statistical torturing that can redeem poorly collected data. All right, let's look at a problem. Researchers conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. Responses were given by a panel of judges. Researchers make the claim that blue enhances performance on a creative task, and then we're asked to test the claim using alpha equals 0.01. Test the claim that blue enhances performance on a creative task. So here's the data. This is the summary data. We always need to check the requirements. The values of the standard deviations from the two populations are unknown and assumed not equal. The subject groups are independent of each other. The samples are simple random samples, and both sample sizes exceed 30. So we're in good shape here. So what we need to do now is go to our calculator and perform the test. So let's clear this out. And we're going to hit stat, test, and this is, because it's a test about a mean, it's a 2-sample t-test. Because we don't know anything about our standard deviations, we're using a t-distribution. So this will be number 4. We don't have the lists of data, we do have our summary statistics. So we're going to go to stats. X bar sub 1 is our first sample mean. Which one of these do you want to call sample 1 and which one do you want to call sample 2? You got to pick a numbering system and then remain consistent with it. It doesn't matter what you call 1. We'll call red because it's on top, group 1, and we'll call blue group 2. All right, group 1. Our mean is going to be 3.39. Our sample standard deviation for the first group is 0.97. Our sample size is 35. For group 2, our mean is 3.97. Our standard deviation is 0.63. And our sample size is 36. And now, do we want to test the claim that's greater than, less than, or not equal to? Well, I skipped a step here. We should have written down our null and our alternative hypothesis. The null hypothesis is that the average creativity measure from group 1 is the same as it is for group 2. Our alternative would be group 1 is greater than, less than, or not equal to group 2. Let's look at our original claim. Blue enhances performance on a creative task. If blue enhances performance, what would we expect to happen here with the scores, the average scores for group 1 and group 2? We would expect group 2 to be greater than group 1 because group 2 was the blue background people. So red would be less creative than blue. Mean 1 is less than mean 2. So we're fine with the less than here. So now we don't touch the pooled. We hit calculate, and here are the results. Our test statistic is going to be what? Our test statistic is this value right here, the t. This number is our p-value. And then our calculated degrees of freedom were 58.1. We could scroll down and get more information, but in order to form our final conclusion, we have enough information here based on the p-value. Is this p-value large or small? What was our alpha level? Our alpha level was 0.01, right? This p-value is smaller than 0.01. Look at the decimal places there. That's 2 thousandths. That's 10,000. Since our p-value is less than our alpha, would we reject or fail to reject the null hypothesis? Reject the null hypothesis, and the null hypothesis said that there is no difference between the two groups. So the conclusion is there is sufficient statistical evidence to support the claim that blue backgrounds enhance creativity. Using the data from this color creativity example, let's do a 98% confidence interval. I just want to show you the difference of how things are going to look if you do a confidence interval for the same thing. Here, this is a 98% confidence interval, so we're going to go to stat, test, and now this is a 2-sample t interval. So we need to go to our 2-sample t interval. 2-sample t interval is number 0. We have the summary statistics. They're still there. They've not changed from what I just typed in. So our confidence level, though, is going to be 0.98 because we were asked to do a 98% confidence level. And now we calculate the results. and this is our output. So we go to stat, go over to tests, and then we're going to go down to 0 2 sample t interval. And this is what we end up with. Negative 1.05 to negative 0.11. And since both the lower and the upper bound are negative, it looks like mean 1 is less than mean 2 because 0 is not in there. There is a significant difference because 0 is not in the confidence interval. So that wraps up section 9.3.